Hello and welcome to this video. In this video we're going to look at alternating current and oscilloscopes. So what we've said in a bunch of these magnetic fields videos is that whenever we have electromagnetic induction, whenever we produce some sort of induced EMF or induced current, it is alternating current. It changes direction. Okay, so this is the major difference between direct current and alternating current. We've also said we use alternating current when we look at things like capacitors back in electric fields. We said they only work using alternating current, they don't work using direct current. And this video is hopefully going to explain a little bit about alternating current, why it's what we're using in all of these cases, and then we're going to go through oscilloscopes, how to read alternating currents and also alternating EMFs. So let's first try and visualize the difference between a direct current and an alternating current. So an direct current means that we have current traveling in one direction, which means that if I were to have a current against time graph, something like this, I'm going to end up with always having a positive or negative current. Okay, I'm never going to switch between one or the other. I'm always just going to have positive or negative. Whereas alternating current constantly changes direction. I will end up having current coming out of one terminal first, and then some time later it switches, and then sometime after that it switches again. So if I were to draw a graph of this, I end up with current against time following some sort of sinusoidal curve. Okay, and this is generally how most currents are. So I'm going to label this I naught. So I naught is just the peak current. And now we have an idea of what direct and alternating current is. Direct current travels in one direction, alternating current constantly flips between two. Notice that the current is going from positive to negative all the time, and obviously this will continue. It will go on for basically as much time as the power source is on for. From this then, we can come up with a general expression for some sort of alternating current. We can say that direct current, we're obviously going to have this single value for, unless we change the resistance or something of the circuit. But alternating current is not going to be a single value. Okay. In order to come up with an expression for this, we know it's going to be sinusoidal. So we could say this is either going to be, let's say I is I naught, and it's either going to be sine, remember this is a time axis, so we need an omega t, or I is going to be equal to I naught cos of omega t. Now, depending on whether it's sine or cos, basically just depends on when you turn the stopwatch on. Because if I were to turn this on at this time, instead of time t equals 0 as it's set here, I would then end up with a cosine graph instead. Okay, so basically what we're getting at here is that the current can change directions. Okay, and we demonstrated this a bunch of times. Now, the key from this is then, if I want to, for example, take a measurement of current in an alternating circuit, I can't just stick an ammeter in anymore, because the ammeter is going to constantly be changing, because as every time changes, the value of the current will change. It's going to constantly be changing from positive to negative. The value is going to change. So I can no longer rely on just having some sort of ammeter in to just measure the current for me. And this is where I have to come into oscilloscopes. And if I wanted to read an alternating current, I would have to use an oscilloscope. Mostly, oscilloscopes are not used for alternating currents. They're actually used for alternating potentials. But since we know that V is equal to IR, I can say that voltage is proportional to current, and therefore I can say that actually I could have a similar expression for the voltage. I have an EMF where I can have either a sinusoidal or either a sine omega t or a cos omega t. Both of these are completely normal. Now, you won't actually have to know these expressions, but these are just there to try and remind you that they are sine and cosine graphs. Now, oscilloscopes, how do they work? Well, on an oscilloscope, you will start off, so let's write here, oscilloscopes, and we've already said these are used for alternating potentials. Okay, now some oscilloscopes are programmed so that you can read current from them. It's not very often that this is the case. Most of the time it's just much easier to use the potential readings. Most oscilloscopes are just used for potentials. But what we can say is that if you've ever seen an oscilloscope screen, they are mostly just a grid, right? So you'll have some central grid that I'm just going to sketch out roughly that looks like this. And then you'll have tiny gaps, which I'm going to draw with these kind of dotted lines. And each of these gaps is a set distance apart. So although my drawing doesn't show it, these are actually equidistant. Okay, so we have these on the x-axis, okay, but this x-axis is no longer going to be just a position. This is now basically we're expecting to see a sinusoidal graph, so this is going to be time. Okay, so this is the time. On your actual oscilloscope, you don't get readings like this. Okay, you just see the screen. You'll obviously have the same kind of things here, but I'm not going to waste time by just trying to draw these out. You will have a specific thing here, a specific distance here for each of these, and on your settings, the thing that you can change is something called the time base. Now, the time base controls how far apart these are. So if I, for example, had a time base of 5 seconds, it means that each gap here represents 5 seconds. Okay, so each one would be 5 extra seconds. I can then change it, so instead of 5 seconds, this is, I don't know, 1 second, then each gap is 1 second. Okay, you get the idea. Each of these represents the time as it goes across. Now, this is a grid, so I can also have the horizontal lines like this, so I end up with these kind of grid squares, or at least they should be squares. They don't really look like squares on my diagram, and these will again be equidistant apart. Now, the time base represents this. I'm going to draw on T here just to show. The second axis here is known as the Y gain. Okay, now the time base obviously is kind of self-explanatory, it represents the time, but the Y gain allows you to choose the potential for each gap. Okay, so for example, if I chose a Y gain to be 5 volts, then each gap vertically is 5 volts. So this would be 5 volts, this would be 5 volts, and so on. Okay, so I'm going to note here that by just saying V. And these are the two settings that you have to be familiar with. When you actually get to do the practical of setting up an oscilloscope, you'll see on the oscilloscope there are loads more things that you can do with an oscilloscope. It's a very useful tool. But for now, we only really need it to read a potential. And so we can set up the time base and the Y gain. And then as soon as we've got this, we want to try and alter the time base and the Y gain such that we observe a single wavelength. Okay, depending on the situation, sometimes you'll want more than one wavelength, but you can set this up however you need to depending on what the experiment is asking of you. But if you set this up to just be a single wavelength, you obviously want this to be as big as possible to reduce uncertainties. So you could end up maybe having a cosine graph that looks something like this. And I've purposely done something here that's kind of a common thing, which is that my axis above and below do not match. Okay, I have two squares on this side. If I were to draw the second square here, it would probably be down here. I only have 1 and a bit squares this side. So when I'm reading an oscilloscope, I have to be very careful as to set my actual 0 point. Now, in order to get rid of that, we don't actually need to set a 0 point at all. We know that on a cosine graph, the magnitude above and the magnitude below should be the same. So we use something called a peak-to-peak reading. Okay, so I have a peak to peak, which means I'm reading the difference on this part here. So I read what the potential is here, I read what the potential is here, and then I take the total distance between those two. So for example, if this is 5 volts here, this is 10 volts up here, and on your oscilloscope you will have smaller readings. So let's say this is 8 volts for argument, or this would be minus 8 volts to be specific. I end up with a peak-to-peak voltage, which we usually write as PP as 18 volts. Okay, and this is generally a good thing to use to try and get the idea of a magnitude of an EMF. However, when we have these oscilloscopes, it's not very useful to have a full trace. Usually we want to put them into some sort of equation, we want to put them into Ohm's law, we want to be able to calculate the power output or the average power output of some sort of component in the circuit, maybe a capacitor. And so we need to try and figure out how do we actually get a single value from a whole cosine graph that is going to actually give us the valid information. And we're going to reintroduce this idea of the RMS, okay? Because we need an average of something that can be both positive and negative. So we have to take into account both the positive and the negative sections of this. And so we basically do what we did before. We square all of the values, we take the mean of all of those values, and then we're going to square root all of those values. If you haven't yet watched the section in thermal physics where we go through that, I'd recommend watching that before you try and wrap your head around RMS, just from this video. I'm not going to re-explain it because it did take quite a bit of time, but it's just an average of vectors essentially. So if I were to take an RMS value here, so I'm going to note this as V RMS, what you will maybe know, for some of you doing further maths, is that if I were to take an average of all of a sine graph or a cosine graph for all of time, okay, so I have this going back to the very beginning of the universe, and then I have it going back to all the way to the very end of the universe. If I take an average value of all of that, I'll get a half. Okay, so my mean of a cosine graph, so my square mean is a half. Okay, what I then need to do is I need to half it, or sorry, square root it. So I end up with this. I know that this RMS value is going to be over the square root of 2. So it'll be something times 1 over the square root of 2. Now, I know that that would be if it was just a general cosine, because it's going to be the magnitude of it, so or the amplitude, which is only ever going to be 1, divided by root 2, right? But in this case, I don't have an amplitude of just 1. I have an amplitude of the peak, which we called previously V0. Okay, so now I have V0, which is the peak voltage, divided by root 2. And again, because I also can do this for current as well, I could also say that I RMS is I0 over root 2. And both of these formulas are on your formula sheet. And the RMS values are what we use in things like Ohm's law if we wanted to go back to that. So these are what we use in Ohm's law and basically any other equation. Okay, these are the values that we use if we want to go back to using all of the DC expressions that we had in AS. Now, what does an RMS actually look like on a diagram? Well, if I was to come down here and say, let's just have this rough diagram of a sine wave, where this is just the potential against time. My RMS value is going to be a constant fixed value because it's just going to be the peak divided by root 2. So this is V RMS. And this is why I can now put this into equations, because this is just an average of all of it. Now, it doesn't mean that I can get a specific power or a specific current or voltage at a specific time, because obviously I know it's going to change, but it does give me an average. So when I put that into these equations, I can get an average power, I can get an average EMF, so on. Okay. So from this video, what you need to take with you is that alternating current is just current that can flip directions. It can be both positive or negative, depending on the direction that it's traveling in. And we can say that this alternating current can be described by sine waves or cosine waves. We can also now talk about oscilloscopes. We know that we use oscilloscopes to be able to measure alternating currents. More specifically, we use them mostly to measure alternating potentials. We have two settings that we need to be familiar with. We have the time base and the Y gain. It's pretty easy to read an oscilloscope. You just look at the amount of gaps that it has, and you use your settings of the time base and the Y gain to basically calculate the stuff like that. What we should mention before we finish the video is that two things that you need to be careful of. The first thing is that if I have a peak voltage here in this equation, remember I said that this peak is not the same as this peak, which means, to be more specific, to take a more accurate peak voltage, you want to say that V0 is actually the peak to peak voltage divided by 2. Okay, now this formula isn't in your formula sheet. It's kind of self-explanatory. If I was to actually line it up so it was exactly halfway between, I should end up with both of them being the same. So it's just half of the magnitude between the two. So this is the first thing you need to be wary of. The second thing is that sometimes they will ask you for a frequency of alternating current, or they'll ask you for a time period of alternating current. And because we have a sinusoidal graph, if they give you an oscilloscope reading, you can basically just read the time period across here. So this allows to read the time period. And therefore we know that T is 1 over F, so you can also calculate the frequency of these oscillations. So this can come up in exam questions. They can give you an oscilloscope trace. They'll ask you to trace out what it would look like if you had a peak voltage of this and your frequency was this. You would have to first work out what your time period is, and then be able to sketch things like this. Personally, I feel like the best way to learn about oscilloscopes is to just use oscilloscopes. If you can, see if you can ask your teachers to just during a break time or a lunch time, if you have a spare 10-20 minutes, see if you can get into the physics lab and just see if you can set up a simple circuit and mess around with the controls and the times base and the Y gain, and see if you can kind of figure out for yourself how these things work. I've given you the general description of how things work, but obviously you always want to get your own understanding and make sure you know how they function, so that it clicks with you. Then we also need to be aware of these RMS values that we can use to then convert back from AC to DC, so that we can put these values of the RMS back into our original equations that we learned in AS electricity. So this then concludes alternating currents and oscilloscopes and magnetic fields. Thank you for watching.